Hello, everybody. So, my name is Arun, and I'm a co-developer of data.table package. And today I want to just talk a little bit about the data.table syntax and give you an overview about, the past as well as the current and the future developments that's about to happen or should happen in data.table. But before I start, does anybody know why the data.table logo has a seal in it? So it's basically Matt's idea, and it's apparently because it makes the RR sound. And it's very fitting, I think. Yeah, so last year I had a talk in Montreal, and this is more or less the first slide I started with. I thought it'd be apt to start with more or less the same slide because it's approximately a year after I presented there. And so at the time I presented, there were about 50 contributors and about 40 releases, and the fact that data.table doesn't depend on any other packages, and about 7,000 and odd unit tests, 93% coverage, which was using Jim's core package. A lot of packages were depending or importing data.table, and yada, yada, yada. And so currently, the good news is that in just about a year, we have about 19 more new contributors, and there's been quite a lot of releases since then, about 8 more releases. It still doesn't depend import any of the packages, I think, except for methods package from base. There's quite a lot of unit tests that has been added, and the coverage has been improved a lot. Most of the contributors, particularly I think Michael and Jan, they've been contributing a lot to a lot of tests that has been missed. More packages are depending on data.table, and it's now the 15th most dependent package as per Meta-Cran. And it's also one of the star packages in R, and more questions on Stack Overflow. And the most important thing is that since the last year, there's been about 370 issues that has been attended to from the data.table package. And in the last 6 or 7 months, 277 of them has been handled. So I'm guessing this is a good sign that the project is more and more active. So with that, I want to talk to you about 3 things today with the talk overview. The first one is a very quick introduction to data.table's syntax for those people who have either not been introduced to it yet or have trouble following it. And the second thing is, over Twitter, I've seen quite a few posts mentioning about the difficulties they have in understanding .sd and .sd call, so I thought this would be a good time to introduce it with, in my head, a simple example. Hopefully it's simple as well for you. And the last one is about some of the optimizations or developments that has been happening in data.table in the past as well as currently. Okay, so the first one, I want to start with a relatively simple example here. We have a data.table with 4 columns, ID, code, val A, and val B. The question is relatively simple. Get the sum of val A for each value of the ID column. In data.table, you'd go about it like this. So dt, the first argument is empty, and then a comma, and you have val A, which is the name of the column in the result, and that equals sum of val A grouped by the ID column. So when you say by equals ID, what data.table does first is to figure out the number of unique values in ID and take the rows and associate them as to what rows belong to each group. So in this case, the first 4 rows and the 7th and the 9th one belong to one group, and the rest of them belong to the second group for ID equals 2. And then for each of these groups, the expression that you provided in the middle, or the second one that gets evaluated. So in this case, the ID equals 1 will have the values 1, 2, 3, 4, and 7, and 9, and the rest of the values go into group 2. And all you have to do now is run sequentially through each group and then compute whatever expression that you provide in the J argument, which is sum val A. So you get this 26 and 19. So if we just make it a slightly more involved, which is get the same sum of val A for each value of ID column, but only for those rows where the code column is not equals B, then the first argument, which we didn't use before, now gets into play, which is code not equals B. So this would basically remove the second and the seventh rows, as shown here. And on those rows, again, by equals ID would group the first, third, fourth, and the ninth rows, and the rest of them will go into ID equals 2. So we'd have the group 1 values to be 1, 3, 4, 9, and group 2 values to be the rest. And again, we apply the sum value for each of these groups sequentially, and we'd get the result 17 and 19. So basically, the 2 and 7 are not in this result. Okay, so the basic idea here is that whatever rows you want to operate on, or whatever rows you want to filter, you provide in the first argument, and whatever you wanted to do on the rest of the rows, you provide to the second argument, and if you want to group by something, then you provide that in the third argument. And if you don't provide the group by argument, then it's just evaluates the second argument directly, and then we're done. So now, if you take a slightly more involved example, which is probably more realistic, if you want to compute the sum of each of the val columns for each ID column, or grouped by ID columns, where code not equals B, the code gets slightly more longer. But let's go through it exactly as we did before. First, the code not equals B part. So again, the second and the seventh rows are not going to be evaluated or are going to be considered. And then we have the by equals ID, which would again group the same way that we have seen before. The first, third, and the fourth, and the ninth column, ninth rows will be in ID equals 1, the rest in ID equals 2. And now we have something called .sd, which basically stands for subset of data. And that contains all the values, or all the columns other than the grouping column in it for each group. So basically, by equals ID here is the grouping column. So we don't have the ID in this data table. And for ID equals 1, we have code, val A, and val B. All the 3 columns, all the values are in there. And ID equals 2, group 2, all the corresponding values of code, val A, and val B are in there. And now, if you notice, there's also this argument called .sd calls equals patterns val, which basically means that only consider the columns that start with val as the columns in .sd. So once you look at that part, the code column goes away. So we are left with only val A and val B for each group. Now we do exactly the same, which is to evaluate the second expression. So for each group, we loop over the columns, and then we compute the sum, which is basically the base function lapply, and you compute the sum on each one of them. So for the first group, there will be a sum calculated on the val A and sum calculated on the val B, and similarly for group 2. So we'd end up with a result like this. So hopefully it's a little bit more clearer about what .sd and .sd calls do, but in case it isn't, there is also a new vignette that was added by one of the contributors to data table, Michael, recently, and you could install the dev version and do vignette data table ASD usage to have a much more clearer and worked out example. And finally, I want to talk about some of the developments that we have done in the past and the future, currently. So if you go back to the general form of the data table, it's relatively clear how to make things faster, more performant. You have to just optimize every single bit of the first part, the second part, and the third part, which is how do you get to decide what rows you're going to do the operations on faster, and how are you going to do the grouping faster, and how are you going to do the evaluations per group faster. So in the past, what we have done to increase the speed for filtering operations is to do something called auto-indexing, which is that, so when you do, for example, DTX% in %, 1,000 to 2,000, here it's a 200 million row, 2-column data table, which is approximately 3 gigabytes. The first run, it takes about 5 seconds. And it's also a little bit longer for the first run, because while it's also doing the subset, it's also creating an index and storing it within the data table as an attribute, so that any subsequent runs on this data table for the column X would be much, much faster. So if I were to run the same expression once again, then it runs in about 0.6 seconds on my laptop. So currently we have the equals and the percent operator optimized for auto-indexing. And about 2 years ago, I also implemented the non-equi-joins, or using binary search for other operators other than equals, which is greater than, less than, greater than or equal to, and less than or equal to. So what would be also nice is to incorporate all those other operators here to have the subsetting for all other operators faster as well. And one other thing what we also did quite a while ago is to parallelize the subset operations across the columns. So it's a basic parallelization. It's a straightforward parallelization. So when you do DT, here we have 20 columns. I just take the first column, which is V1, and ask for the rows which is greater than 50. By default, it's running on 2 threads. It takes about 0.6 seconds, and if I run it with 1 thread, then it'll take about twice as much. You can't expect a lot of speed up here because it's still cache bound. So in this case, we end up with a speed up of 1.7 times, which is still pretty good. These two features, auto-indexing as well as the parallel subsets, has been there for quite some time. But more importantly, recently there has also been some developments in the by argument of data table, which is very important because it decides the number of groups that you have and which rows belongs to what group. And this is usually a very compute-intensive operation. And data table has always been using radix ordering to find these groups. And so far, we had just radix order, not parallelized, and Matt Dole, the main author, went ahead and parallelized it completely. So now it runs on my computer with 2 threads twice as fast, or almost twice as fast. And so basically, you can just keep using the same code that you are using, and you just get the performance benefits depending on the type of computer that you run on. And so far, I've talked about the optimizations that we did in the first argument, which is the rows, and the last argument, which is the group by. And the second argument, where all the computations take place, is also one of the places where we can do a lot of optimizations. We have implemented quite a few functions internally to speed up the computational part. So for example, when you have, let's say you have a 20-column data table with about 50 million rows, when you do something like lapply.sd mean, which basically for each column V1 computes the mean of all the other columns, all the other 19 columns by group, what this does internally is to use the function mean that data table has implemented in C, so that it doesn't have to go back and forth between R and C for evaluating the basis mean function. So you can see the difference here if we just switch between the internal version as well as the external one. So Jan has gone ahead and implemented quite a few functionalities recently. One of them is NA-fill, which basically here it takes the last observation and then it carries it forward. So here, the previous observation is 2, and it's carried forward here. There is no previous observation in V3, so the NA is intact. And if you want to learn more about this, you can look at !NA-fill. And you also get twice the speed up because it's also parallelized on the number of columns. And there's also other functions like froll sum and froll mean, and more functions coming up in the rolling category. It basically does a rolling sum, but it's just implemented in parallel. So with a window size of 3, it runs through each columns where taking the first and the second one doesn't have 3 values before them, so it would return the value NA. The third row has the value 3, and the previous 2 values are 1 and 2. The rolling sum is therefore 3 plus 2 plus 1, 6, and so on. And this is also parallelized. And another one, which is a correlation function. I'm going to skip it, and you can have a look at question mark correlate to do what it does. So basically, there's a lot of improvements that have been done in the I, j, and the by arguments, and a lot of people have worked on it. There are also new vignettes added and bugs fixed. I want to thank quite a lot of people here for their work. For example, fwrite's gzip argument was completely submitted as a PR by one of the contributors. There are quite a few other people who have done a lot of issues regarding auto-indexing, following up on Stack Overflow regarding bugs and so on. And the people who are also testing every single day with the development versions on their production code. I don't know how they do that. Also, Cran team as well as GitHub CIR developers who make our process of developing packages and fixing things when some things break quite easily. And Michael for a lot of contributions regarding documentation as well as R and C code. Jan for quite a lot of functions, and he's also comfortable with C and OpenMP so far. And of course, Matt for everything regarding data.table. And thanks to you for your attention. I'll take any questions.
So we have time for 1 or 2 questions.
Hi, thanks for the talk. I have a very specific question. Is the unique n function, the one for counting the number of unique values, parallelized too? Because I need it for some heavy computation. It's quite slow compared to all the other functions. So
yeah, so internally it depends on data.table's ordering, so radix ordering, so it should be parallelized automatically as well. Yeah, but in case, just to be sure, I can follow up with you after the talk.
So we have time for 1 more question.
Hi, Arun. Thanks for the talk. I don't have a question, but I just want to say thank you for this amazing package with Matt. It saved my master thesis handling huge amounts of data.
Cool. Thank you.
Let's thank Arun again.
Thanks very much.